So we're very happy to start OSMU 2026. Apologies for this delayed start. There are some things which were not under my and Michael's control, so kept getting delayed. So this is our first talk. Very happy to welcome Dr. Nathan Secrest. He is an astronomer at the U.S. Naval Observatory, and his research focuses on active galactic nuclei, quasars, and the large-scale structure of the universe. He received his BS in astronomy from the University of Hawaii at Hilo and completed his PhD in physics at George Mason University, where his doctoral work investigated supermassive black holes in dwarf and bulgeless galaxies. Nathan has also held research positions at the US Naval Observatory and worked with facilities including NASA Infrared Telescope and the University of Hawaii 2.2-meter telescope. Nathan is widely known for leading a series of influential studies on the so-called cosmic dipole anomaly, using all-sky surveys of quasars and radio galaxies to test the cosmological principle and the standard ΛCDM model of cosmology. His papers in 2021 and 2022 reported statistically significant large-scale anisotropies in the distribution of distant quasars and radio sources, and these findings have generated substantial interest and debate in the cosmology community, which is what we'll hear about today. And lastly, Nathan has also contributed importantly to work on quasar catalogs, celestial reference frames, and astrophysics of active galaxies. Over to you, Nathan. Pleasure to have you with us.
Thanks, Ginger. Yeah, that was a wonderful introduction. Yes, again, my name is Nathan Secrest. I am at the U.S. Naval Observatory. So most of the time I work on the latter research on celestial reference frames and geodesy. But every now and again, I get a little bit of free time and they let me work in cosmology and don't complain about it too much. Today, I am very excited and honored to be given an opportunity to talk about an anomaly which really, in my opinion, uh, needs to be taken quite seriously because it really points at potentially a foundational issue with not just the standard cosmology, but all cosmologies that are based on the assumption of isotropy and homogeneity. So this anomaly has been called a few things in the literature. I prefer to call it the cosmic dipole anomaly. I think it's sufficiently accurate without placing preference on any interpretation. But today, I think would be a good time to really review the status of research and kind of future directions. So, if I will let me advance the slide here. Oh, there we are. So yes, just a little background. So the foundational assumption of the concordance cosmology or lambda CDM is that the universe is at least statistically homogeneous and isotropic on large scales. And these are scales sort of the order of a couple hundred megaparsecs or so. And importantly, if we assume isotropy and homogeneity, that allows us to use the FLRW metric. And that basically relates the evolution of the universe by a simple scale factor, this a sub t. And that's governed by general relativity. So it allows us to solve Einstein's equations exactly, or at least analytically, and that yields the Friedmann equations. So it's a very nice approximation. It makes the math simple and tractable, especially in the early days when we didn't have access to high performance computing. So other interesting things come out of this assumption. One sort of conspicuous example is the so-called cosmic sum rule, which implies suggestively, if not somewhat dangerously, that if you know other constituent properties of the universe, like your matter content, your curvature, and so on, that out of that, almost for free, you get a value for the cosmological constant, lambda. So, of course, this isn't the only evidence for lambda, but um, it is an interesting property that is allowed under lambda CDM or allowed under an FLRW type cosmology. And so using the cosmic sum rule and independent estimates for omega matter, assuming curvature is basically zero, radiation as negligible contribution, you get a universe that is dominated by a cosmological constant. You get omega lambda of zero point 0.7. So the foundational assumption, this is all to say that the foundational assumption of isotropy and homogeneity is not just a simplifying one that makes the math tractable, but it also potentially has profound implications for what we understand the content, the structure and content of the universe to be. And that kind of leads to a foundational question, in my view at least, and that is what physical properties or quote unquote physical properties of the universe depend on this assumption of at least statistical isotropy and homogeneity? Can you have a cosmological constant without the FLRW metric? What is the meaning of the scale factor and quantities that are defined using it? For example, the age of the universe. Like, what is the age of the universe if the universe is not isotropic and homogeneous? So, how do we infer that the universe is indeed isotropic and homogeneous? Well, one big indicator is the cosmic microwave background. This is an image from the Beyond Planck collaboration. It shows the CMB, or at least at the CMB frequency. You, of course, see the contaminating influence of our galaxy along the galactic plane. So this is in galactic coordinates. But you also see this very striking and conspicuous dipolar component with an apex pointing sort of in the direction indicated there. The simplest explanation for this dipolar component is that, well, it's predicted if we are moving with respect to the CMB, which in the concordance cosmology we almost certainly are. And our movement is the vector sum of several independent velocity components, or to a lesser extent, our motion around the sun, but the sun's motion around the galaxy's motion with respect to the local group, and so on. And so, making that interpretation, you can correct the CMB and you can perform this process called in-painting to handle the galaxy. And from that, you get the beautiful CMB map that most people outside of cosmology are very familiar with. And from that, you get the anisotropies of order 10 to the negative 5 in strength. So you have a 10 to the negative 3 order CMB dipole. You make the kinematic correction, assuming that it is purely kinematic, and you get down to the fundamental anisotropies, and you can start to do cosmology with your model. So it's all very clean and all very obviously very important. The question is, though, the CMB is a redshift 1100 structure. If the cosmological principle is correct, this foundational assumption, then the rest frame of the universe at more local redshifts should be the same as the rest frame of the CMB. How do you test this? Well, a very elegant solution was provided by Ellis and Baldwin in 1984. And the way it works is analogous to the way we measure the dipole in a CMB, except now we're measuring source counts above some flux. And it turns out that there is an exact prediction for the number of source counts, the modulation of source counts you should see across the sky for a given flux cut and a given velocity, so long as you understand the rate in which you see an increase in sources at fainter fluxes. That's given by the parameter x, that's a power law exponent, and the mean spectral index of your sources within your passband, either in radio, say 1.4 gigahertz, or at other passbands, say in Ys in the W1 band, if within that band you have more or less, on average, a power law spectrum. That will give you an exact prediction for the dipole amplitude you should see in the number counts for a flux limited survey. And so this formula that's um, uh, in the box on the bottom is often called simply the Ellison-Baldwin formula. To my knowledge, this is the only paper that Ellison and Baldwin ever did together. So it's very nice shorthand. And importantly, the dipole should be the same in all catalogs of cosmological particles, galaxies, quasars that move, quote unquote, move in Hubble flow, provided that the cosmological principle holds. So this is a very powerful independent test. Well, that was 1984, and back in 1984, we didn't have any catalogs with suitable statistical power. Given the strength of the dipole, which is of order 0.5% for radio galaxies and really most objects, you won't be able to beat down the noise, the mainly shot noise, until you get to catalogs of order 500,000 sources or more. And so no such catalog existed until the late 90s with the advent of the NRAO VLA Sky Survey, or NVSS. So that provided a nearly, not quite full sky, but most sky survey of radio sources at at 1.4 gigahertz, which allowed for the construction of a catalog of radio galaxies of size about 500,000 sources. So this is a nice image of, it's a Hilbert map of the NVSS. You can see, of course, there's some galactic synchrotron contaminants along the galactic plane, but they're fairly contained and fairly minor. And just for reference, the predicted direction of the CMB dipole is indicated. So again, your predicted amplitude is of order 0.5% for NVSS 0.45 times 10 to the minus 2. But what's interesting is that the first studies, which came shortly after the publication of NVSS, found somewhat larger dipole amplitudes. The first study was published by Blake and Wall in 2002. It was a Nature paper. And they found that the dipole amplitude was of order sort of 1 times 10 to the minus 2, maybe upwards of 2 times 10 to the minus 2. This really kind of depends to an extent on your choice of masking of what how you're making the estimator flux cut. So there's some variance systematically or methodologically, but pretty consistently the dipole is pointed near the peak of the CMB dipole, but a factor of 2 to 4 disagreement in the inferred velocity. Interestingly, this paper reported consistency with the kinematic prediction, but this consistency was based on essentially taking an average of results for a range of flux cuts. The NVSS, the limit of the flux limit of the NVSS depends on declination mainly because of the change from the D to DNC hybrid configuration of the VLA during the survey. So even though the sort of nominal flux limit of the NVSS is of order a few millijanskis, in practice it's a 10 to 15 or so. So a range of flux cuts was tried, and essentially the average statistical significance was taken. But the issue with that is, of course, as you go to higher flux cuts, your significance goes down. So it's not really a meaningful metric. But what is a meaningful metric is the significance of the result using a flux cut that allows as many sources in while having a minimum of unexplained variance. And so I've outlined that in this table from Blake and Wall, where you can see that for a flux cut that gives a reduced chi-square to the dipole model of unity, you get a dipole amplitude that's about twice as large. So in this paper, they used 2 times D as the metric. So you can read that as 1.1. Again, the prediction is of order 0.5. So it really showed a 2.2 sigma tension. Later analyses combined the NVSS with other catalogs like SUMS and RACS, and it generally reinforced this indication of a too large dipole. So this at the top right is a figure using SUMS and NVSS from Jacques Collin's 2017 paper. Other radio surveys have known systematics, so you have to be careful. This is a figure from Natasha Hurley-Walker's 2017 paper on the TGSS, comparing the TGSS fluxes, which are low frequency, 150 megahertz, to the Gleam survey. So some surveys, especially at low frequency, below a gigahertz, it starts to get, you have to be very careful when it comes to flux systematics. So not all radio catalogs are created equal, but the nice thing is that it's usually pretty easy to readily spot the effect of systematics. But the point is that these earlier studies using radio galaxies consistently found a dipole that's about 2 to 4 times larger than that expected from the CMB. The results, however, were at modest significance, typically about 3 sigma. A wide range of estimators was used at first. There hadn't yet been a convergence on which estimator is the least biased or the most efficient, perhaps. So Searle harmonics, the so-called linear estimator, least squares, which involves explicit template specification. Each of them have their own biases. The results are also mainly using one survey, NVSS. Now, all surveys have systematics. The NVSS, again, has a systematic respective declination. What's interesting, though, is that the NVSS is such a widely used, and I would say quite venerable survey at this point, that the declination systematic seems to be the only one identified in the literature. Last I checked, there were over 5,000 citations to Jim Condon's NVSS paper. And of those citations, none of them indicated any issue with like flux calibration systematics, which again affects surveys like the TGSS. So other than the declination systematic, which was recognized immediately, the NVSS is an amazingly clean survey. So the results, even though they are largely based on the NVSS, should by themselves be taken somewhat seriously. There's the other issue with where exactly these galaxies are. What's their redshift distribution? Because you can get a dipole contribution from local clustering. So local generally, at least in a lambda CDM universe, means a redshift less than 0.1, really less than 0.05, where you can get a significant contribution from local clustering. The Blake and Wall paper attempted to remedy this by, in fact, I believe that paper was the one that coined the term clustering dipole, by removing objects from the IRAC-Z catalog, which were mostly nearby infrared selected objects. And so, it seems at least that papers that have removed at least identifiable nearby objects, Jack Cullen's 2017 paper is another example using 2MRS, it doesn't seem to be very sensitive to it, but it should be pointed out that at least with radio galaxies, formally speaking, the redshift distribution is not very well constrained. So that leaves, these sort of modest significance results with open questions about clustering, leaves some questions. How statistically significant really is the result is obviously a big one. But another question is really, can we do better? Or at least, can we really check this result? Again, most of the result was based on NVSS. So do systematically independent catalogs exist of moderate redshift objects that could potentially confirm this anomaly? And that's where the Wide Field Infrared Survey Explorer, or WISE, comes in. This was a full sky space-based infrared survey between 3.4 and 22 microns. And importantly, and I really can't emphasize this enough, is that it's systematically independent from ground-based radio surveys. Totally different wavelength, different detector design, different scanning law. It's in space instead of strapped to the ground. There's no atmosphere. There's really nothing systematically in common between WISE and radio sources. So any result that we get from WISE can safely be treated as a systematically independent check. So this is kind of where I come in. I began working with Sabir's group in 2019 when I happened to be in Paris for unrelated reasons. And the interest was, could we use the All WISE catalog, which was an early co-edited version of the WISE catalog, to look at cosmologically distant objects to explore the dipole? I had published in 2015 a catalog of quasars using all-wise data. And this catalog mainly was for the purposes of basically calibrating the frame spin of the Gaia catalog, which was going to be published in a year or so. But it wasn't really meant for cosmological purposes. And but nonetheless, we explored the catalog and looked to see if it was clean enough that we could get a signal out of it. And it turned out it really wasn't. The number of scans that had gone into All-Wise wasn't sufficient to even out issues with like moon contamination and so on and so forth. So we were kind of beating our heads against the wall about this, and miraculously, I think right as we were about to give up, this new co-added catalog, CatWise 2020, came out much, much deeper than All-Wise, especially in the W1 and W2 bands, which are bands most sensitive to emission from active galactic nuclei and quasars. And of course, it's much deeper in those bands because those are the only bands you can still observe in after your cryogen runs out. So we started working with CatWise 2020. And so as I mentioned, the W1 and W2 bands are very sensitive to AGN activity. This is a WISE color diagram from Ned Wright's 2010 paper on WISE. And it shows where the different objects sit in color parameter space. And what's nice is that all the stuff you don't want, stars, nearby elliptical galaxies, nearby spiral galaxies perhaps, all fall below a W1 minus W2 cut. That's 3.4 minus 4.6 microns. That's quite clearly definable. In fact, a cut already existed prior to the study, thanks to Daniel Stern. And it turns out that you can make a cut of zero point 0.8. And you basically, all that's left are QSOs, Seiferts, and Eulers. And Eulers are arguably powered by AGNs. You may notice that there's some cool T dwarfs in there, but the dwarf stars, T dwarf stars are generally so faint that in a catalog as uh, deep as WISE and pointed away from our galaxy, they're not a significant concern. So, what are the results? Well, we produced a new catalog. Interestingly, it had about the same number of objects, which I systematically tried to avoid confusion on in our publication. But the catalog has 1.4 million quasars. That's almost a factor of 3 as much as the NBSS results. And what did we find? So the kinematic prediction is similar to for radio galaxies, a little bit higher. But we found that, again, the dipole amplitude is about a factor of 2 too large. But because of the large number of objects, we were able to reject the kinematic null hypothesis at quite nearly 5 sigma, 4.9 sigma. And so this plot on the bottom left shows the distribution of predicted dipole amplitudes under the kinematic null hypothesis. And in red, it shows what we found. And on the right shows a quadrant of the sky plot. So this prediction was based off of the noise properties of the survey, of the catalog, and so it's a frequentist analysis. So instead of seeing the contours around the result, you see the contours around the prediction. But they're basically equivalent. So we did a lot of sanity checks looking for trends with ecliptic latitude, which is the principal axis of WISE, and I'll mention that a bit more in a second. Galactic latitude, you can have issues with stellar contaminants. So we ended up having I should say stellar contaminants aren't really the issue. It's the confusion noise that's caused by stellar contaminants. So you get a decrement in sources at lower galactic latitudes. So we ended up seeing such a decrement, and that was predicted beforehand. That was already a known issue with WISE. So we made a cut along the galactic plane, plus or minus 30 degrees, and recognized a trend with ecliptic latitude. But with these systematics recognized and mitigated, you get a very clear dipole signal in your map, and that's showed in the rightmost plot, where you see a smoothed version of the top plot, and there's a very clear dipole signal there. And so this was the result from our 2021 paper, which has become fairly well known, thankfully. But there's been some independent confirmation. So there was a paper by Dom et al. In 2023 performing a Bayesian analysis of the same catalog. And they used a more sophisticated likelihood. They used a full Poissonian likelihood where we had used like least squares. They assumed uniform priors. They marginalized over the ecliptic latitude trend that we had identified. And they found an even higher excess over the kinematic prediction, almost a factor of 3. And because they found that higher access, correspondingly, the significance was also higher at 5.7 sigma. But this was a nice independent confirmation of the results of our results. So at least from a methodological point of view, it didn't seem that we were too off. So we have radio results and we have quasar or mid-infrared results. Can they be combined? Well, luckily, radio galaxies and quasars are basically completely different types of object. Radio galaxies tend to be evolved, quote unquote, red and dead, as they say in the extragalactic world, massive ellipticals, by and large. Quasars, on the other hand, tend to be hosted by bluer, gas-rich disk galaxies. So as a result, the overlap between these two populations is fairly minimal. And so for our second paper, which we published in 2022, we did a joint analysis between NVSS and WISE. We found that the two populations overlap by only about 1.4%. That's promising. So what did we do? Well, NVSS was a smaller catalog, so we decided to give the shared sources to NVSS. And in so doing, we produced completely orthogonal catalogs. Now, it's important to reiterate here that not only are the surveys orthogonal, space-based, mid-infrared, wide survey, ground-based, radio, uh, VLA sky survey, um, but the objects themselves are also orthogonal. We are looking at a different population of objects now. So we liked the frequentist analysis that we did. Of course, the Bayesian analysis gave very similar results, but we decided that it wasn't sufficiently general because, in a sense, it placed more preference or significance on dipoles that were aligned with the CMB because we were interested in the kinematic null hypothesis. But we realized, well, if the dipole is too large, maybe we shouldn't overinterpret what we're seeing. Maybe we should essentially account for the variance in direction. Now, the variance in direction has very minor effect, but it is an effect in terms of the significance of the dipole. And so we decided to define a two-dimensional p-value that's based again on the C and B direction, but instead of simply the amplitude, now we're looking at also the C and B offset. So you can define these contours that are 1 sigma, 2 sigma, and 3 sigma. But because it's a larger parameter space for null hypothesis simulations, it produces a much more conservative estimate of the p-value. So in other words, you can have a 3 sigma rejection along a wider contour than simply one dimension. And when you do the simulations, you end up having more null hypotheses that cross a certain threshold. So this is our result. These figures show the actual p-values. And you can see that the NVSS p-value is of order 2.6 sigma. That's not too far off from previous results. The WISE p-value is a little bit lower. As I mentioned, the effective direction is fairly minor, but it's there. And so we get a 4.4 sigma rejection as opposed to a 4.9 sigma rejection. That's fine. But because these are independent results, truly in every way imaginable, then you can combine them quite easily in the frequentist framework using a weighted z-score. And so the weight comes from the number of objects, and you have the z-score for each survey. And so that shows, at the bottom left shows the z-score and the weights for NVSS and WISE respectively. And when you combine them, you get a 5.1 sigma rejection. So obviously highly significant. It was also the first time, formally at least, this predated the Dom paper by 1 year, formally at least, that we exceeded the 5 sigma threshold for the dipole anomaly. But I don't really put much stock in 5 sigma, 6 sigma, so on and so forth, because sigma doesn't mean anything if your systematic errors are unknown. But this result accounts for systematic errors by using orthogonal catalogs from orthogonal surveys. So in this case, I think it really needs to be treated quite seriously because it'd be an astonishing coincidence if the independent systematics of NVSS and WISE conspired to give such a significant result. One might say, well, fine, but that's still a result dominated by WISE. What about radio? Can radio pull its weight perhaps a bit more, and you can have a joint test that is a little bit more evenly distributed between the two domains? Well, now you can, thanks to some innovative methodology by Jonah Wagenfeld in 2023. They developed a multi-Poisson maximum likelihood estimate with a novel term to account for survey non-uniformity. So it allows them to essentially work with a deeper flux cut than they normally would be able to. So they can maximize the source counts in their estimator, and of course, that would increase the significance. So they were able to reject the kinematic expectation at a level of 4.8 sigma, comparable to our 2021 WISE only result, using only radio data. They find that the dipole is probably aligned very closely to the C&B dipole, which is consistent with the result that we found, at least if we don't attempt to deconvolve the dipole excess from the kinematic contribution. I'll mention that again in a second. But this, importantly, is the highest rejection using only radio data. There is a more recent paper doing a joint analysis of NVSS, RACS, and LOTS DR2, which are all radio surveys. And that yielded an even higher significance, 5.4 sigma. So this was Bohm et al. 2025. And again, this result is independent of WISE. So with WISE, we're at about 5 sigma, 4.4 if you're being really cautious. With radio, you're at about 5 sigma, at least in joint radio analyses. This is quite a strong signal we're seeing here. All right, what about other wavelengths? What about visual wavelengths? Well, a couple of years ago, a new visual wavelength quasar catalog called Quia was released. This combined data from Gaia and Unwise to develop a quasar catalog with spectrophotometric redshifts. A quasar catalog that was largely meant to do cosmology, at least on smaller angular scales. And so immediately, Vital et al. Used the Quia catalog to test for the dipole. They initially thought that they found a dipole amplitude that was consistent with the kinematic expectation, but it turned out that they had actually overestimated their spectral indices, and as a result, overestimated the kinematic expectation. So I reached out to them, and we were able to identify the issue, and they put out an erratum that basically says, well, the visual wavelength results are not inconsistent with the kinematic expectation, but they're also not inconsistent with the dipole excess. So at visual wavelengths, it's kind of, but there's a reason. There's a reason why this would be. And that's because of galactic reddening, basically. A very hard cut, even with the selection function that was provided with the Quia catalog, which was based on a Bayesian method. They still had to make a very, very hard cut on the galactic plane to get any kind of signal. And this is expected at these shorter visual wavelengths. And I'll talk about that again in a little bit. So again, as I mentioned, the Quire result neither favors nor disfavors the dipole excess. So my take, since I have the bully pulpit here, is that the orthogonality of the radio galaxies and quasars suggests, if you do back of the envelope math, a joint significance of the cosmic dipole problem exceeding about 6 sigma. That, again, is based on this weighted z-scores method. So, 6 sigma, orthogonal catalogs, I think it's pretty clearly established that we're seeing something. And so, what is that thing? That's the big question now. Well, we don't know, but we can start to say what it decisively is not. What it decisively is not is inaccurate kinematic prediction. Shortly after we published our papers, a few papers came out looking at the possibility that not accounting for source evolution or redshift evolution could skew the predicted kinematic dipole. I have to admit, I don't personally understand how this argument works, but people smarter than me do. And what we found, this was a paper led by Sebastian von Hausliger, what we found is that so long as you measure the spectral index and that exponent x I mentioned earlier, which relates the source counts with flux, at the flux limit, or the flux cut, then the Ellison-Baldwin formula holds exactly, independent of the distances or histories of the objects. And intuitively, this makes sense, right? The Ellison-Baldwin formula is fundamentally based on special relativity. It's just Doppler boosting and aberration. So special relativity is quite uninformed as to the histories of objects. It just cares about where the objects are and how fast they're moving. So intuitively, this makes sense because the dipole modulation is happening at the flux cut. You're not going to see it without a flux cut. So the result that is implied by intuition is now confirmed, has been proven rigorously, thanks to Sebastian's efforts. But more importantly, measuring alpha at the flux cut, alpha and x at the flux cut, was already done in previous works based on our intuition. So source evolution is irrelevant to the dipole problem, is the takeaway. There's also questions of the shape of the source's spectrum. At radio wavelengths, you get generally a synchrotron spectrum, at least at lower frequencies. And that's going to be power law, although you can get some curvature terms, of course. But what about the mid-infrared? Mid-infrared, you're looking at redshifted emission observed at 3.4 microns. Maybe there's spectral features, absorption features. It's not immediately obvious. But the important thing to remember is that only the mean spectral index is what matters. And because you are taking the mean observed spectral index, you're looking at the average of spectra that are observed over a wide range of redshifts. So if you use theoretical quasar templates, for example, and you randomly sample them according to the redshift distribution, which for quasars is well known, then you find that the average spectrum that you're looking at is quite close to power law. And so this was a figure and a result that we showed in our recent RMP colloquium, which this talk corresponds to. So it's probably not that. Well, almost certainly, decisively is not that. Now, what it almost certainly isn't, survey or methodological systematics. It was recently claimed, based on the ecliptic latitude trend, which is quadrupolar in nature, that an excess octupole systematic in the Catwise 2020 data could mimic a too large dipole. This was some work led by, in a paper led by Abgari et al., showing that when you include these higher modes, includes especially the octupole, that the distribution of dipole amplitudes can reach levels where perhaps the measured dipole is not so significant. Is this a concern? No. The reason is because that result was obtained by arbitrarily allowing the quadrupole and octupole power to match that observed in the dipole. There's no evidence for that at all. We can measure the power spectrum wise, and we do, and we have recently a paper that Sebastian led with this figure, the power spectrum shown here. I have indicated the position of the octupole. And so this figure shows the power spectrum with and without the ecliptic latitude trend. And you can see that, of course, while the quadrupole term, the term before it, varies dramatically depending on whether you apply that correction, the octupole term is basically insensitive to it. There's and it's an upper limit. That's a downward arrow. So there's no effort. There's no evidence, I should say, to support an excess octupole at all. It's undetected. The only systematic that is detectable in the WISE catalog is the ecliptic latitude trend, which we expect because that's the principal scanning axis of WISE. So WISE coverage is generally shallower at the ecliptic latitude, at the ecliptic equator, I should say, and much deeper at the ecliptic poles. And that actually produces counterintuitively an excess in sources at the equator and a decrement at sources at the pole due to the Eddington bias. And I think I do mention that later on its talk. In fact, I do in the next slide. So we had argued in 2022 qualitatively that the ecliptic trend is due to deblending at Eddington bias. So the more common bluer AGN, so if you just cross-match like the SDSS quasar catalog with WISE and look at their WISE colors, most AGNs are actually bluer than the cut we use. The problem is most everything else is also bluer, so we have to make a hard cut to get rid of everything else. But because they're more common, at lower signal to noise towards the equator, the ecliptic equator, they will preferentially scatter into the red cut than scatter out of it because there's just more objects. That's called the Eddington bias. A recent paper by Oda and Lewis recently showed quantitatively that the ecliptic latitude trend can be simulated. It can be reproduced given the WISE scanning law and the signal to noise of the data. So this is a nice figure from their recent paper showing the real data up top and the simulated Eddington bias in the bottom. So qualitatively, it makes sense. Quantitatively, it makes sense. And it was also expected. Another piece of evidence against this issue is that because it's signal to noise based, the ecliptic latitude trend disappears at higher flux cuts. So the question is, what happens to the dipole at higher flux cuts? We had looked at this without formally publishing it previously as a sanity check, but we decided in the colloquium to formally publish that result. And so this shows this plot on the right shows the dipole, the WISE quasar dipole amplitude and direction as a function of cut on W1. And you can see that while the dipole might drift a little bit, and that might not be systematic, that might be astrophysical, the amplitude stays consistently elevated. In fact, in terms of this significance, it almost doesn't matter that we use such a deep cut. But the cut wasn't based on an attempt to get the most significant result. It was just based on where we started to see evidence of uncontrollable systematics. But the point is that the excess dipole is robust. You can make quite a harder cut on flux and you still get it, where the ecliptic latitude trend basically vanishes. So if the ecliptic latitude trend were related to the dipole in some way, if it were responsible for the excess dipole in some way, then the dipole should fade away at brighter flux cuts, or the signal to noise is much higher. This is not seen at all. So we are certain that the ecliptic latitude trend, which has been the principal systematic of contention in the literature since we published our paper, we are quite certain it has nothing to do with dipole excess. So it's important to reiterate that this dipole anomaly, which is consistent between radio and the mid-infrared, has been confirmed using multiple facilities, independent facilities with their own systematics. The mid-infrared and radio results are especially independent, with no shared observational systematics and basically no shared sources. So new work will probably continue to identify systematics that were not explicitly addressed in previous work. But in my assessment, it is highly unlikely that this dipole anomaly will, as many researchers hope and observe, and some other with other anomalies, to sort of die a death by a thousand cuts, where new data, new methods slowly dwindle down the statistical significance until it's not significant anymore. I very highly doubt that's going to happen because as new data comes in, as do and more sophisticated methodologies are developed, the anomaly is getting worse. It's not getting better. So newer work again has generally continued to support the anomaly and increase its significance in more than just a statistical sense. Another thing it almost certainly isn't is frequency dependent. So frequency dependence was proposed by Siebert et al. In 2021. They were looking at radio data, but the trend with frequency that they proposed was basically entirely justified by TGSS, which, as I mentioned earlier, has known flux calibration systematics. I mean, if you make a
Hello,
plot of
can you hear me?
TGSS, I'm sorry, Sabir, you were speaking? Okay. Um, if you make a sky plot of the TGSS, you can see them by eye. So it's not a subtle effect. And moreover, recalibration, if you use the NPSS to recalibrate the TGSS fluxes, the excess basically disappears. Now, there's been complaints that that's kind of putting the cart before the horse. NPSS already shows that dipole anomaly. I personally don't understand why flux calibration would necessarily cause the issue, but it's worth pointing out. But it's also worth pointing out that the functional form proposed by Siebert entirely misses the Wise value, which was not included in that fit. So this plot here at the bottom right shows is one of the plots from our colloquium, and it shows the radio data points as well as the Wise data point and their weighted average in the shaded gray with the kinematic prediction range hatched. So the functional form is proposed by Siebert completely misses that. And you can really see it's TGSS that kind of is justifying it. So I wouldn't put too much of your research efforts into looking into that further, but of course, we can't completely rule it out. What it most likely is not is incorrect velocity with respect to the CMB. So the CMB velocity is not just based on the observed dipole in the CMB, it's also based on the modulation of multipole power that is due to motion. So independent estimates, but estimates not based on the dipole by itself, of the velocity with respect to the CMB using the CMB anisotropies has consistently found that the canonical value of about 370 kilometers per second is about right. Plus or minus 50 to 100 kilometers per second, maybe. So almost certainly the kinematic, our motion with respect to the CMB is accurately known. What it maybe is, I've talked a lot about what it isn't, what it maybe is, an intrinsic matter dipole. So in our 2022 paper, we decided to look a bit further than joint significance, and we started by deboosting the NVSS and WISE catalogs. So again, we're pretty sure the CMB, the velocity with respect to the CMB is fairly accurate, so we use that velocity to deboost the two catalogs. And what we found is that they have a residual dipole, about 0.9 times 10 to the minus 2, that's pointed quite far away from the CMB dipole, about 40 degrees or so. And what was very interesting, it was a tantalizing result, was that while the NVSS and WISE dipoles are consistent, that consistency actually improved further by deboosting them. Hmm. So that would suggest, if that's true, if it's reflecting something real, that you're looking at some kind of intrinsic dipole. So Wagenveld et al. In 2025 did a more thorough, in my opinion, joint analysis using NVSS, RACS, and WISE, but they found basically the same thing. They found a residual dipole of the same amplitude pointed basically in the same direction that we found. So, we're consistently finding a residual dipole offset from the CMB direction by 40 to 50 degrees. And a 40 to 50 degree offset is statistically indistinguishable from a random, if you just randomly sample directions on the sky, the offset from any given direction, it's not significant, that offset. So it doesn't seem to have any relation with the CMB dipole anymore. So Jim Peoples took some issue with this idea. In a review he published in 2022, he stated that if quasars and radio galaxies were useful mass tracers on scales approaching the Hubble length, when the observed dipole anisotropies are order 0.02, that would have produced a bulk flow on the order of 2% of the speed of light, which is absurd. Okay. But that 0.02 value is based on the observed dipole. So it's not including the effect of motion with respect to the CMB. Well, okay. Well, if we deboost, we get a residual dipole now of order 0.008. Is that so absurd? I don't know. But it's certainly worth pointing out that, this would be quite a contentious issue. So is that such an absurd idea? Well, what it might be, differing rest frames, perhaps. This is the tilted universe scenario. So recent work completely independent of the dipole analyses, has confirmed that the observed velocities do not, in the local universe, do not uniformly converge to the Hubble flow beyond the local clustering distance. So this is the cosmic flows analysis, for example, Watkins et al. 2023, using CF4 data, infer a bulk flow of order 10 to the minus, with a chance of order 10 to the minus 4 of happening in lambda CDM. So this is the plot showing the various bulk flow components as a function of distance. And they suggest that this could be an indication that the particle rest frame of the universe, which is, of course, what we'd be measuring with the radio galaxies and quasars, is not the same as that inferred from the dipole and the CMB. And they also point out that their results are in line with the cosmic dipole anomaly. So this is very interesting, and I think worth looking into. So where do we go from here? Well, it'd be nice if we could measure the dipole of regular galaxies, radio galaxies, which are HN dominated, and quasars they trace the underlying matter distribution at varying levels of bias. So we think that regular galaxies are probably much higher fidelity tracers of the distribution of dark matter. So it'd be interesting to see if dark matter shows the same dipole, whatever dark matter is. And also radio galaxies, or I should say regular galaxies, are largely independent from radio galaxies and quasars. Radio galaxies and quasars are a few percent of the total population of galaxies. So it really provides a third independent population. So we could also use better signal to noise. And while we're, at least I'm pretty sure the cosmic dipole anomaly is real, the question is it really a dipole? Is it a true dipole? We've set limits on the higher modes, but the limits allow for some power in the higher modes, certainly. Where does it actually point? Can we accurately deconvolve velocity from matter? And get redshifts. This dipole excess, again, CMB is at a redshift of 1100. The radio galaxies and the quasars are at a redshift of sort of 1 on average. The dipole excess is rising somewhere. And so now the effect of binning on redshift on the Ellison-Baldwin formula has been quantified exactly, thanks to uh, Sebastian and Charles Dong's recent efforts. So future surveys, Rubin LSST, now observing the sky. Advantages, it's a true synoptic survey at visual wavelengths. So Quia was a mix of Gaia and Unwise. So it was a little bit of a hybrid survey. And not really quite synoptic. Oh, I forgot to mention that Quia was also based on quasar counterparts identified by Gaia. So there's a little bit of a mysterious selection function in there. So now we have the possibility of having a true synoptic survey at the requisite depths to look at this. So we're going to get 4 billion galaxies, not quasars. So again, it's going to be a third independent source type. And we're going to get pretty high accuracy photo-Zs. Some disadvantages. So I mentioned this reddening issue. The problem is that the total to selective reddening ratio, which is called RV, is not well characterized outside the galactic plane. So this plot at the top right shows values of RV measured out to 4.7 kiloparsecs. And you can see that it's really confined within the galactic plane, where the total dust content is high. And therefore you can get a good signal. So the commonly assumed constant of 3.1, for example, will cause large-scale systematics that will limit the precision of the dipole measurement. So when you make your flux limited catalog, you have to correct for reddening. We did this even with Wise, even though it was very insignificant effect. And so that contains the reddening coefficient, which is known to, a percent, say. It's based on the passband, basically, of your detector or your filter. It's based on the color excess EBV. That's measured directly from dust emission. So there's a nice map, for example, from the Planck collaboration. And then the total to selective extinction or reddening ratio RV. That's usually assumed to be 3.1, but it varies by almost 0.2 dex across the sky, and it's not correlated with EBV, so it can't really be predicted. So I decided to look into this somewhat quantitatively. I've begun simulating skies at the LSST I band using CAM. And the top left plot shows an example of a simulated sky with the effect of reddening and a choice of RV selected from a normal distribution centered at almost 3.1. It's about 3.3. So you can see very clearly the effect of reddening on the source counts, but also the source counts are very high. So that's quite exciting. So, so you can perhaps ask the question, can you figure out a way of correcting the map that will allow you to pick up signal on low multiple scales like the dipole? So if you use a constant value, as is typically the case in the literature, you get a map like the one on the right. So this is using the mean value of a random instantiation of RV, which was estimated by essentially fitting the power spectrum of the RV map within the galactic plane, but allowing it now to be to vary across the sky in some random and unknown way. But if you just assume the mean value of your simulations, then you get a correction that looks like the one on the right. And that map looks pretty clean. I think anybody would be quite satisfied if they corrected their photometry and got a map that looked like that. But turns out it's not good enough. So if you inject the kinematic dipole into the initial simulation, and then you redden your map, correct it using a naive constant value of RV, and then remeasure your dipole. Not even injecting things like shot noise, just the map reddening naive correction. The distribution of the dipole amplitudes in kinematic units in the I band, which is the primary band for LSST or Rubin LSST, is shown in blue. And so for the kinematic null hypothesis, the amplitude distribution is huge. And more to the point, it can't rule out the value from Wise and radio. So this is in the hatch shows the joint value from Jonah Wackenfeld's paper. And so even though the simulations have the kinematic null hypothesis as the injection dipole, the recovered dipole uh, cannot rule out the excess that we see. I should point out that there's a subtlety here. So this is not a posterior distribution. This is the distribution of found dipole amplitudes, observed dipole amplitudes, given unknown RV, with the statistical properties of RV that are known. So in other words, we may find that the dipole in galaxies from Rubin SST looks consistent with the kinematic expectation. It may be near ratio of 1. But that is not significant. It is not meaningful because that result could be just a chance result from the distribution of RV. Likewise, we could find a value completely consistent with Wise and radio, near a value of 2. That would also not be meaningful. No matter what we observe, unless we can quantify RV across the sky, no matter what we observe with Rubin SST, it will not mean anything. I can't emphasize this enough. For the sake of sanity, I've done the same simulations with the H-band, which is like with Euclid. In H-band, you can make meaningful statements. The kinematic expectation is expected to fall within a range that can potentially rule out the Wise radio dipole, or confirm it. Now, of course, I consider it confirmed already, but again, this is looking at galaxies now, which is a third population type. And then again, for sanity check, the green shows the Wise passband, which is very tightly constrained. So this is full, lambda CDM CAM simulations here, including local clustering, but only in the near and infrared without knowing RV, do you have the methodological power to probe the true dipole. So this is something we talked about somewhat qualitatively in the colloquium. Since then, we've been looking at this quantitatively. And I don't think I can say it enough that until we have a full sky map of RV that we have confidence in, or we have some way of marginalizing over RV, which is a non-trivial task I've been trying, whatever amplitude, if somebody says, hey, we've got this new we've got 4 billion galaxies now. Let's look at the dipole, and they assume RV of 3.1. Whatever they find will mean nothing. And it sounds harsh, but it's true. So I just thought I would belabor the point here a little bit. So what's our best bet without knowing RV, which we may be able to quantify using novel methods. I would say Euclid, honestly. Euclid is has a sufficiently red operating wavelength that we can deal with not knowing RV that well. And it also has a slightly wider sky footprint. There's also Sphere X, which is collecting data. That's going to be useful for spectrophotometry. So it potentially could give us redshifts, but it's limited in depth and resolution, quite similarly to WISE. So it will also be affected by source confusion towards the galactic plane. And it's limited to a similar flux level as well. But it gives you 104 spectrophotometric bands. So potentially you can start to get some redshift information, which is very important, clearly. The square kilometer array. If we can get rid of local sources, because once you get down to, so radio is a little bit tricky because the deeper you go into radio, you're not just picking up more radio galaxies, you actually start to pick up star-forming galaxies that are much local. There's very strong cosmic evolution of radio galaxies. This is a result known since the 80s. And so once you get below about a millijansky, your radio galaxy population, your radio source population becomes dominated by nearby star-forming galaxies. So if there's some way that you can really get rid of those, if you can get H1 redshift, say, then potentially you could measure the dipole within 9%. This was a paper by Bacon et al. 2020 that showed that. That would be useful. But a takeaway here is that there's been a lot of recent interest in the Allison-Baldwin test. Again, no catalog existed suitable for the test until 1998. And this is reflected in the citation patterns for the paper. So the paper is published in 1984, very few mentions of it, very few citations to it. But then along comes NVSS. The Blake and Wall result paper misleadingly says that it's the radio galaxy dipoles consistent with the kinematic expectation. And that probably slowed down progress a little bit. But then later analyses found that there actually, in fact, is a problem. But then with the advent of WISE, or the WISE analyses, basically confirming, yeah, there's really a problem here, and we need to figure out what's going on, then there's been this explosion of interest in the Allison-Baldwin test. In fact, half of all kinematic dipole work have happened in just the last 3 years. So my point is, I want you to work on the cosmic dipole anomaly. It's one good use of AI is I can get Uncle Sam to say whatever I want. And as the token American here, I feel like I've got the right. So let's solve this problem. Let's work on it together. I'm interested in everyone's perspectives. So just some concluding results. FLRW-based cosmologies like lambda CDM now have a critical foundational problem because the cosmological principle appears to be strongly violated. There really is no way for the cosmic dipole anomaly to exist in an FLRW universe, that I know of at least. The dipole problem is getting worse with new analyses and data, which is opposite the trend with spurious anomalies. Redshift evolution, I haven't mentioned lensing, but there have been some looks at that. Lensing, remaining systematics are not helping to relieve the tension. So what we need is to understand the physical nature of this problem better. Is it only radio galaxies and quasars, or is it all matter? Maybe Euclid can help us with that. Maybe Rubin LSST can help us with that if we can beat down the systematics at visual wavelengths. Is there really kinematic mismatch, or is that a fundamental anisotropy? Both. What about redshift tomography? What about the high redshift universe? These are all things that we could potentially explore in the coming years. And I think that it's really a very exciting time to work on this problem. So I'll just leave this slide, which is a bit cheeky, just reiterating the British statistician George E. Box saying all models are wrong, right? It's true. Even what we see with our eyes is a model. And if you don't believe me, look at some visual illusions. But some are useful. Clearly, some models are useful. And so the thinker is what quantities, in quotes, in the universe might be artifacts of model choice. So I found this, one of the April Fool's papers this year did a spherical harmonic decomposition of a cow, and I just couldn't help myself. I had to include it. But we do these mathematical parameterizations of what we see, but that doesn't make it the cow, right? What we're looking at fundamentally doesn't care about our math. So anyway, I'll leave it at that. Questions, complaints?
Yeah, great. Thanks so much, Nathan. It was really beautiful. I loved it. Very clear. And I think it brings the problem into sharp focus. By and large, I think everybody will agree that there is an anomaly. And the question then is, the debate is now, what is it implying? So I think we are going to have a great discussion. Andrew, go ahead, please.
Thank you, Nathan. That was really a fascinating and I must say quite persuasive talk. I heard quite a number of talks talking about anomalies, and this one seems quite interesting. Now, while you've been talking, I've been thinking about what you say and wondering where could this possibly come from. And I'm wondering that since these patterns in a standard inflationary model are laid down during the epoch of inflation, and that the modes we see from the cosmic microwave background exited the horizon earlier than the modes that exited the horizon that produced the quasars and the redshifts you're looking at. And this is a dipole, which is sort of the lowest order besides the monopole, that could leave an imprint from inflation. And I haven't thought about this for more than half an hour, so maybe I'm completely crazy. You've thought about this for much longer. But could it be that some dipole pattern that's existing during inflation would be responsible for that pattern? Because if that's true, and I'm just off the top of my head here, that would be some very interesting information about what happened at the beginning of inflation.
Yeah, I mean, at first blush, I suppose I don't see why not. I will caveat any replies by saying I'm not a theorist, so I'm decidedly an observationalist, and I'm much more comfortable in answering data and methodology questions. But I know that there has been part of the explosion of interest in this test has been an explosion of theoretical papers that have come out. And it seems to me like the interpretation of choice, or at least the more commonly endorsed one, seems to be this idea of a tilted universe. And I suspect, it's just an inclination, that the anomalous bulk flows that we see, which is an independent result, is probably related to this in some way. But that's all I can say. And I would love to see any work that looks into this idea that the dipole, the particle dipole, as the CF4 paper says, could have been imprinted at a somewhat later epoch. I think that'd be really interesting to read.
So, can I follow up on that? Could tilted mean exactly what I just said?
It might be, yeah. I really don't know. So I'm happy to discuss any idea with the caveat that I am not.
Andrew, I was just thinking about what you said. Could we say that maybe we started homogeneous and isotropic, but then nonlinear structure grows in a way that we misunderstood, that it does allow these large bulk flows, although we began FLRW. Lambda CDM can be wrong. I mean, that's okay. But is the cosmological principle wrong? That's more serious. Anyway, we can come back to this just for sharing my thoughts. Yeah.
Well, I mean, there is this kind of slight wishy-washy quality to this question, right? I mean, is the cosmological principle wrong? Yes. I mean, we know that from the fact that we exist. So the universe is not perfectly isotropic and it's not perfectly homogeneous. The question is, what model is tractable at the level of isotropy and anisotropy, the level of isotropy and homogeneity that we see. And so the statistical isotropy and homogeneity allows for lambda CDM so far, but this dipole anomaly does not.
Okay. Before I go ahead, I think there are two comments. How do I see yeah, Roya said, Andrew, will it not also produce quadrupole and octupole? You have to. Okay, you replied, we do see an anomalously large L equals 2 in the CMB. Yes, large dipole is supposed to be kinematic, not from inflation. You all want to take this further, or should I go to Anthony's question?
We don't see a large quadrupole. We see no quadrupole in the CMB. I think, Andrew, you got it the wrong way around. Sorry to interrupt, but there is no quadrupole in the CMB.
Andrew's agreeing. Okay, so maybe we can go ahead, Anthony. We'll come back, Andrew, if you have more things to say. Anthony, go ahead, please.
Okay, yeah, thanks very much for the talk. Very interesting. I'm particularly interested in the question of the direction and how things line up. And for the first part of the talk, you were emphasizing that really, the different dipoles did line up. And then when we got to looking at the p-values, NV, SS, and Ys, I don't know if we go back to those plots. These are the color contours with p-values for those two things.
Oh, sure, yeah.
Yeah. So it appeared to me there that there's already evidence in those diagrams for a prepared offset away from zero in the dipole direction. If I'm understanding these plots right, should I be taking it that there's evidence for about a 30-degree offset in MBSS and 10 or 15 in Ys, or is that a misreading?
No, I think that there is some evidence, certainly. It doesn't really become significant until you further allow for the true sort of kinematic
Sorry,
velocity.
one moment. Is somebody else getting a mic noise?
I think we might have a hot mic there somewhere. But this was one of, let me see if I can, it was over here. Oop. Yeah. So this plot here in equatorial coordinates shows the residual dipole direction and amplitude posteriors. So if you allow for the CMB velocity, then you get a then you get this residual offset, which is significant.
Okay, but I'm just trying to understand whether in these early plots earlier in your talk for NV, SS, and Ys, we are indeed seeing evidence for it having a non-zero offset.
Oh yeah, so I would say very marginally.
Ah,
So maybe the more useful plot here might be uh, skipped it here. Might be this one. So this was from our 2021 paper. And so the at the bottom there, the right quadrant, sky quadrant plot shows the frequentist distribution of dipole directions under the kinematic null hypothesis for Ys. And I don't think I mentioned that that is the 95% confidence contour. So we are finding a dipole amplitude that not quite at the level of a 95% significance offset from the CMB, but you know, maybe. So,
yeah.
so by itself, by themselves, there's some tensions observed. It is kind of a mix, and that again, that's expected. That's not a concern. The dipole direction is statistically the hardest to constrain. The amplitude gives a much higher signal in the fits.
I'm asking because I think the type of explanations one would try and come up with would vary quite significantly if it was both the direction and the amplitude which were different and not just the amplitude.
Absolutely, absolutely, and that's one of the reasons why it's so important to be careful with these exciting future surveys, um, because we don't want to because we want to measure whatever this dipole is, and again, it might not be purely a dipole. We want to measure it with much higher signal to noise so that we can determine, does it have higher modes? What is its structure, and where is it pointing? In my view, I think Euclid probably gives us the best chance of that in the near future. But yes, is the intrinsic dipole fundamentally pointed in a different direction from that of the CMB? That is a major question. I'll point out just to avoid confusion here, that this result that we found in 2022 and Jonah found in 2025, that assumes that the motion with respect to the radio galaxies and quasars is indeed the same as that of the CMB. So it's not the same as the tilted universe scenario where the motions are different. So if you assume that CMB and radio galaxies and quasars share the same frame, which is consistent with the cosmological principle, you find that the dipole amplitude is much larger than allowed by lambda CDM, which is inconsistent with that principle. And you also find that the dipole is pointed about 40 to 50 degrees away from the CMB dipole. So it's a little bit of there is a degeneracy of interpretation. You can have the same velocity and produce a quantified estimate of an intrinsic dipole, or you can try to simultaneously estimate the velocity, but you don't have the signal to noise. So,
Subir, could you please say your comments? I think that'll be more useful if you could come online and take part in.
Sorry, I didn't want to interrupt. I just wanted to clarify that, as Anthony can comment better, that the L equal 2, the quadrupole mode of the CMB, is well known to be anomalously low. In fact, it is consistent with 0. But whether that is really true of the original quadrupole or it is because of the galactic mask used, which which subtracts off maybe the real quadrupole, is not clear. In any case, it is consistent with cosmic variance, so we don't like to there's nothing to discuss there. We might be so positioned in the random Gaussian field that we don't see a large quadrupole from our position. That's possible, but we certainly don't see a large quadrupole in the CMB sky. In fact, what we see is consistent with 0. Anthony, would you like to comment?
Yes, indeed. We have an anomalously low quadrupole.
Yeah.
I personally think it may have something to do with inflation, and the power spectrum that comes out maybe is a reflection of a turn down in the primordial power spectrum. But yeah, it's very difficult because it's the usual thing. We've got one universe.
Yes.
And so trying to estimate, a quantity like that is really tough from one sample.
Yeah, but to address Andrew's concern, it is true that it is, quite interesting to contemplate if this could be an inflationary relic. The problem is that it cannot. Well, you talked about perturbations, Andrew. It cannot be an adiabatic perturbation because that is strongly constrained by the CMB. We did look into if it could be a isocurvature perturbation, a superhorizon isocurvature perturbation. This was the original proposal, actually due to Jim Gunn many years ago, which was then developed by Mike Turner, and that is what led to this idea of this tilted universe. However, on looking at it carefully, we found that such a isocurvature perturbation cannot in fact affect the matter dipole. It can only affect the CMB dipole. So that then means that any explanation for this anomalously large matter dipole would have to be fine-tuned if it was in terms of an isocurvature perturbation, because then the fact that the two dipoles are consistent in direction would have to be taken on as a coincidence. There is no reason for them to be related. So in other words, we could be moving at twice the speed that we think we are from the CMB dipole, and half of that is being cancelled by this isocurvature perturbation suitably aligned. But then you might ask, why is it aligned just so as to do this? And I looked at the odds of this happening because, as Nathan said, the angular alignment or misalignment is actually quite poor. It's of order 30-40 degrees. So the chance would only have to be a 1% chance, which may be acceptable to some, but I would find it quite contrived to argue like that. So this is in a paper by Dominic et al. I'll paste it in the chat, in which we showed this. And although that idea can be looked at a bit more, it also predicts a small non-zero quadrupole. It does appear fine. What you want is a mechanism that will affect both the CMB and the matter dipole together, because that would then naturally explain why they are in the same direction. So any mechanism that addresses one but not the other is not really satisfactory. Okay, that's all I have to say. Thanks.
Thank you. Thank you. Anthony, something more?
No, that's it for the moment. Thanks.
Thank you.
Can we hear more from Roya?
Yeah, please, Roya, go ahead.
I really, Subi said everything. So I just send you this paper in which there is this isotropic mode that Subi was referring to. And it actually says that if you have this isotropic, there would be some signature on the quadrupole. That's what I was saying. But I mean, you are saying maybe, I mean, I'm not disagreeing with you. Maybe you're saying that there are some sort of inflationary models in which you only produce the dipole. That could well be. I don't know. Yes.
But then why haven't we seen it in the CMB? The point is there is a constraint on any intrinsic dipole from the good match of the aberration induced in the higher CMB multipoles. And the velocity you get from that agrees with the velocity that you get from the kinematic interpretation of the CMB dipole. I mean, you can argue about how many sigmas, and but the point is they are basically consistent. Yeah. So that doesn't leave much room for the intrinsic CMB dipole, and that's what.
I'm not sure whether Andrew is referring to the intrinsic CMB dipole. I think he's talking maybe something like isotropic mode that doesn't produce any quadrupole or octopole or high multiples in some sort of inflationary scenario. I have no idea. There are so many different inflationary scenarios. Maybe that is possible.
Well, I'll say it's got to be either adiabatic or isocurvature or mixed.
It can be isocurvature, but the problem with our isocurvature is that it gives you the quadrupole, right? I mean, the one that we worked on with Dominic.
Yes.
But Andrew is saying, okay, why does it have to be a scenario that gives also higher multiples?
Yeah, I just want to. What I'm trying to say is that the dipole that's generated in the CMB. I agree with what you say, Subir, about the dipole is generated at an earlier time, exits the horizon at an earlier time during inflation. So there's two different times that.
I see. Sorry, I misunderstood. I understand now. Okay. So it's a super horizon dipole. It's not yet entered our Hubble radius.
Yeah.
But in that case, the paper that Roya cited, that we actually worked together on that is relevant. That shows that such a perturbation, because it will convert into an adiabatic mode once it enters the horizon, so it is strongly constrained by the CMB then. As long as it is on super horizon scales, that is not relevant. But we find that such a thing would not affect the matter dipole at all. It would only it would only affect the CMB dipole. And then the question arises as to why should the CMB dipole and the matter dipole then be aligned? Okay, they're not perfectly aligned. They're only aligned within 30 or 40 degrees, but still, they do seem to be reasonably well aligned. That is the sticking point.
Yeah, but in our model, we also had predicted the existence of higher multiples.
Yes, a very tiny one, but that would be quite hard to detect. As it is, even with the dipole with a few million. Well, okay, maybe in the far future we can detect a quadrupole. Yes, that's possible. The CMB quadrupole in our model would be actually is the value of this coefficient experimentally, this A20, that is to say L of 2 M of 0, that is less than 10 to the minus 5 at 3 sigma, and we had predicted a value of about 8 × 10⁻⁶. So it is currently it is below the upper limit. Basically it is fairly undetectable in the CMB because of cosmic variance and so on.
Yeah, I should maybe
Yeah.
also sort of reiterate that I think this is really where redshift tomography is going to help out. So I may have given the impression that LSST is going to be useless, which is not the truth at all. I think what LSST is going to give us is redshifts. It's going to give us, I mean, you're going to be down to 25th magnitude. You're going to get redshifts for basically everything, including objects in NVSS and WISE. And that's going to allow us to do to really trace out how the dipole depends on redshift. And there's been some very early preliminary evidence, at least one paper that I can think of, that suggests that there might be a redshift dependence. So I don't remember the author's name, but there was a paper a couple of years ago showing that the redder objects in the WISE quasar catalog have a dipole that is shifted in a significant way in direction from the bluer objects, which have a dipole that's closer to that of the CMB. So you do get a systematic shift. Now, the color of WISE quasars is largely a function of their redshift. You get a general reddening of quasars out to a redshift of about 2 before you get turns over and starts becoming bluer again, but by then you've run out of sources.
Was this Panwar et al. With Pankaj Jain
Yes.
and
Yeah,
right, yeah.
right, yeah.
But that wasn't statistically significant, was it?
Well, so the shift in direction was.
No, the correlation is reddening.
No, it was. I mean, I actually verified this myself.
Okay.
So you do indeed see that when you break up the WISE quasars by the color, their WISE color, so we start at 0.8 as their cut, that you get a shift in the direction of it. I think that's interesting and worth exploring further. It might be a systematic effect because, again, the Eddington bias comes into play, and the exact value of the Eddington bias is almost certainly going to be dependent on color. But the fact that you see that, I think, is worth investigating further. And color is, naively at least, a function of redshift for quasars, especially for quasars. So I think really redshift tomography is going to give us the insights that we clearly need to make progress here.
Sure. Well, I hope you sort it out, because I had proposed that we do a dipole test with the LSST data, and after your damning remarks about reddening, we kind of gave up on that. So,
well, yeah, I mean, it's not great.
Yeah, if you show the previous plot, that looks pretty good, right?
Looks great, right? The
Yeah,
plot on the
yeah,
right looks
yeah.
like, wow, what a perfect all sky plot. Let's do cosmology.
Yeah.
It turns out that the signal we're looking for is at a level that our eyes can't pick out so easily.
Right.
And what's interesting is that without appreciating the uncertainty in the total extinction coefficient, this would almost certainly result in years of papers by people complaining about unknown systematics in Rubin LSST. Or let's say that the observed dipole in Rubin LSST is consistent with, appears to be consistent with the kinematic expectation, which is allowed by the simulations in large cases. Then the false conclusion will be drawn, well, this highly statistically powerful survey, 4 billion galaxies, pulls out the anomalous dipole, so the whole thing was big on, and then Lucidium is safe. That's something that I'm getting out ahead of right now to make sure that we don't waste decades of valuable time on basically barking up the wrong tree here. I mean, this is a systematic that we have to understand is present with visual wavelength surveys, especially.
I don't think you have to spend so much time, because SphereX should be releasing its data within a year, and that's well, essentially an update of WISE. And at least, even if you didn't seem so enthusiastic about it, but surely given that they will give us redshifts to 1%, it will already be a considerable progress in identifying where this anomalous dipole is arising.
Yeah, I mean, absolutely. If the redshifts from Sirius are precise enough, and I think they will be down to probably W1 of 16 or so, a little bit shallower than our data. But again, the dipole anomaly does not depend that much on our flux cut. It persists even at very bright flux cuts. Then that's not the right slide.
Yeah, the previous one, yeah.
Then yeah, we should be able to get, at least on average, by averaging spectra across multiple sources, perhaps in the Hale pixel, say.
Sure.
We should be able to get to do some redshift
Yeah.
tomography.
The point is simply that data is already in the can. They finished their first full sky survey last
Yeah, they just
year.
need to make it easier to work with. Now you have to query every
I
object.
agree,
It
but they
takes
have a commitment to make all that data public within 6 months of finishing the survey, which is
it's
wonderful. I
it
mean,
is currently extremely tedious to work with your X data. I have tried.
yes,
Hopefully that'll get easier.
yeah.
Nathan, I have a question. So we can say that yes, there is an anomaly, dipole anomaly. But does it imply that on the surface of last scattering of the CMB, the matter distribution was not isotropic already? Does this follow?
The matter distribution was not isotropic at the surface of last scattering. Well, I mean, even
we
in
don't,
lambda CDM, that's true to some degree,
but
right?
in general, we don't know that, do we? I mean, we are seeing what we are seeing at redshift of 1.
Yeah.
CMB is at a redshift of 1000.
My point is, it probably could have started out isotropic,
Yes.
and then structure growth happened in a way which, let's say, is perhaps inconsistent with lambda CDM. But I don't call this a violation of the cosmological principle. It is that with structure growth, maybe such directed bulk flows can.
But that is precisely a violation of the cosmological principle, TP,
No,
because
in the past it was obeying it.
but we don't know that. What we can only judge by what we observe from where we are.
Yeah,
And I'm
no.
saying,
Okay,
so
so well, that's what I'm asking.
yeah.
Is do we understand the growth of structure under gravity well enough to say that there was already a violation of the cosmological principle on the surface of last scattering?
And you get
So
it as a package, right? Lambda CDM is a theory of structure formation,
let us
and
rule out lambda CDM is ruled out. Let's say fine.
then no, keep the CDM part at least because we do need a theory of structure formation. Otherwise, we won't know how
No,
structure
maybe
can be.
maybe something like Mond, or we don't understand growth. What I'm saying, we don't understand growth of. That's my question to you. Would would gravity already rule out uh, isotropy on the surface of last scattering? That's
I
what
think
I'm.
let's say Anthony has a comment.
Yeah, yeah.
Let him
Anthony,
speak
please go
first.
ahead. Please go ahead.
Well, it's sort of a comment about the question of gravitational instability in developmental structure, which is, I wonder if you know about the result that if you stack this microwave background temperature at the position of voids, in particular supervoids, and then you ask what's the average temperature difference you see from non-void positions, you get about 4 or 5 times the effect that you'd predict. And this is at some significance, like about 4 sigma. I think the first person to call attention to this was Granite back in 2008.
Actually, Granite et al. Claimed that they had seen the late ISW effect, and Anthony, it was in fact my students and I, Seshadri Narathur and Sean Hotchkiss and myself, who pointed out that it was actually anomalous because the expected signal is sub microkelvin, whereas Granite et al. Had detected 9.8 plus minus 1.8 microkelvin, which they claimed was a 5 sigma detection of late ISW effect. but it in fact is, as you say, anomalous. In fact, we established it to be well, it was not huge. It was about 4 sigma anomalous compared to what you expect. But
Yeah.
that anomaly, as you know, has persisted. This was with WMAP 5 and SDSS, can't remember the DR4, I think. And then Planck confirmed it, and that has continued. In fact, Isvan Japudi gave us a review of the situation 2 years ago at that meeting of the Royal Society. I don't know if you came for that.
Hmm.
And the anomaly persists. You're quite right. There is a problem with understanding large-scale structures, and in particular, this shows up. As you said, in the cross correlation with the CMB, we see temperature changes which are 10 times bigger than what you would expect from the late ISW effect.
Okay, I'm not sure about 10. Maybe, let's say 4 to 5.
Well, our initial estimate of the late ISW effect for the kind of voids,
Yes.
you're right. The kind of voids which you expect in lambda CDM are well prescribed because we know what the distribution should be. For them, the average decrement we computed was minus zero point 0.5 or zero point 0.5 micro K. But then you have to allow for the fact that you select these voids using an algorithm called Zobov, which has a certain selection effect. And if you take all that into account, then you expect of order 1 micro K, and you are saying something like 10 micro K. So that is the factor of 10 I alluded to. But if you take into account the uncertainties, it is no more than 4 sigma at best.
Yeah.
Yeah.
Okay, I
So,
raise it because it's
Anthony, sorry, Anthony, my question was, let us assume the CMB is primordial. Then, knowing from the temperature and isotropy, we have an upper bound on the density in homogeneity. Given that, can we say in a model independent way that the anomaly and the void kind of large scale structure we are seeing today is inconsistent with the primordial interpretation of an isotropic CMB at the last scattering surface?
I don't know about that. I'm not quite sure I got the picture you're putting forward. I mean, what can I just
I
say?
want to I want to think outside of lambda CDM. I'm happy to accept that lambda CDM has a problem. Let's say that. But does isotropic CMB on last scattering is already in trouble because of the data that we are seeing today, in the sense that does gravity rule out such growth of structure in a model independent way? Uh,
Hmm. Because we don't know the origin of this effect, and I don't think we can say whether it rules out that at all.
yeah.
I guess my question would be, does the surface of last scattering tracing the inhomogeneities that became a structure later, how model independent is that?
Yeah, that's the point. Yeah, right. Let's say given general relativity, or maybe even given MON, for example, does a situation like this, let's say, rule out MON also? I'm not clear about that.
To be more compellingly, this anomaly means that all the analysis that are being done today, which
Hmm.
assume FLRW to analyze, I don't know, supernova Hubble diagram, etc., or for
Yeah.
example, the more recent data from DAISY or baryon acoustic oscillations, they all assume FLRW, notwithstanding this over 5 sigma discrepancy that shows that that assumption is not cannot be taken for granted. This is more urgent because it means that we really need to ask whether FLRW is now a safe assumption because
Yeah,
uh,
that's where I am a little uncomfortable with your stance. Maybe we know how dark matter tells us how structure evolves. Maybe it is not dark matter. Maybe it is something, which will then evolve structure from FLRW at the last scattering epoch to what we are seeing now, the anomaly. I mean, that's
no,
my
no, hang
question.
on. I don't think I made myself clear. we are observing quasars, and their reference frame in which they're isotropic is not the same reference frame in which the CMB is isotropic. But this assumption is crucial to the analysis that are being done, for example, on DAISY data to infer, I don't know, time varying dark energy or whatever.
Yeah. So, but
So,
again, you might rule out the dark energy interpretation, and I'm separating all that from the assumption of primordial isotropy, which, let's say, gave us nucleosynthesis, Big Bang nucleosynthesis. I mean,
yeah, at early times, there is no problem with having FLRW. For example, Big Bang nucleosynthesis is perfectly consistent with
yeah.
FLRW.
So
CMB decoupling is perfectly consistent with FLRW.
perfect. So
So that
when
then,
does
sorry, go on.
FLRW begin to get violated in your scenario?
The first, it's not, we don't have a scenario, we only have observation. So our observation is based on quasars at a mean redshift of 1.2. Their FLRW is definitely violated. What
That
happens
I
between
agree.
1.2 and 1000 we don't know because we haven't observed there.
Yeah, so all I was saying was
Yeah.
that if you allow me
Uh,
isotropy at 1000 Z,
yes.
I'm okay. I'm okay.
No, no,
Uh,
hang on. That is not okay. The isotropy at 1000 Z is already obvious from the CMB. We see
right.
only small fluctuations there and a dipole which can be attributed to our local kinematic motion, right? But the big problem which Nathan talked about is that that would then require the rest frame in which quasars and galaxies are to that is assumed to be the same as the rest frame of the CMB. After all, they were in thermal
Yeah, I
contact.
agree.
Yeah,
But
and
my
so that 5 sigma discrepancy we just heard about means that this nice cozy picture breaks at some point
I
between
agree.
redshift of 1 and redshift of 1000. Now,
Maybe the
how it
law of gravity, maybe the law of gravity allowed the development of a large bulk flow, which is what
possibly,
you are saying.
possibly. So that
Yeah,
is
yeah, that
all
is
things that we need to find out, and we can
yeah,
speculate
yeah,
about it. We
yeah. I
need to
think we
find
are
out.
in agreement.
But
We are in agreement.
yeah, yeah. But the more immediate, urgent, essential issue is that meanwhile, we, that is to say, the entire community, with some one or two exceptions perhaps, in which I include myself, are going on saying that the universe is, two-thirds of the universe is made of dark
Yeah,
energy, and that dark energy now has not only a constant part but also a z-shift
yeah,
dependent part, and all these conclusions are being drawn by assuming that FLRW holds exactly at the present epoch for the objects that are being observed, which has been
yeah.
falsified empirically by this
Yeah,
Ellis Baldwin test.
this is the third point,
Yeah.
independent of growth of
Yeah, yeah,
structure.
independent of all that. This is purely
Yeah,
empirical. It's just saying
yeah,
that the entire basis for the analysis that are being carried out today with superb data, I mean, the DAISY data is beautiful, no question, but they are analyzing it using a model that has just been shown to be falsified. I don't really understand this. I don't understand how people can do that, except I must then conclude that they don't take this dipole anomaly seriously. And I hope you will all agree.
can we do an interesting exercise if you
Yes,
don't mind? I asked Claude about this,
yes.
Anthropics Claude. I want Nathan, could you please kindly stop sharing for a moment?
Yeah, yeah, yeah.
I want to show you. So Claude says that when Subir extends this to conclude that dark energy is not there, that Claude will push back on. That interpretation does not follow. So let's see what is being said. So just for can you all see this? Can you all see the screen?
Yes,
Yeah.
I can see it.
Yeah. So here it says the work is rigorous, persistent, etc. Reviews of modern physics. But I would not describe the cosmological principle as being in trouble in the sense what is in trouble. So it says something. It's contesting the interpretation that supernova cosmology's interpretation of dark energy is problematic. So that's what I want to understand. Why is there a pushback on that issue?
On which issue specifically? I'm sorry, I didn't quite.
Let's say Sarkar's stronger thesis is that if our local frame is not the CMB frame in which in the way lambda CDM assumes, the inference of cosmic acceleration from supernovae 1A itself suspect.
Hmm.
This is the conclusion most of the community pushes back on the hardest. I mean, what are the reasons for this? So this guy says that what is
Sorry,
the
that's a different topic and a different talk. I think we
no,
should.
just want to show you this. The
Yes.
naive treatment of frame transformations in low Z supernova cosmology is in trouble,
Yes.
trying to say that cosmic acceleration is there, like allowed by multi-probe convergence CMB plus BOA.
No, but they are not multi-proof convergence. They all assume FLRW.
Yeah,
So it's not that they're independent in that sense. The data
that
sets
I
are
agree.
independent.
I agree with you.
But it is not at all true that there are multiple independent bits of evidence, etc., because you are analyzing them in the same framework. The bottom line of that is the FLRW framework, and the FLRW assumption rests on the cosmological principle, which you have just seen is falsified. So, regardless of what Claude thinks, let us just
No,
deconstruct this.
I'm not giving Claude
No,
higher
Claude,
ground.
of course, is just scanning the internet and picking up things
Yes,
at random. The
yes.
point is the following, that what it is referring to here, just in case that has caused confusion, is we have also written papers in which you look at the acceleration that is inferred from the supernova data. And I should say that rather than a million objects in supernovae, you have only today of order 2000 supernovae, but that is still enough to analyze the diesel acceleration parameter, give it angular dependence and see if it is isotropic. Now, first of all, I should emphasize this, and this is not sufficiently well appreciated, at least in the astronomical community, that any property of the quantum vacuum has to be isotropic, otherwise you violate Lorentz invariance. So, you know, even if it is bleeding obvious to anyone who studies fundamental physics, let me state that, because it is not actually very well known, it seems to me. So, if cosmic acceleration is due to the vacuum, due to cosmological constant, dark energy, whatever, it has to be isotropic. But what we find when we look at the acceleration inferred from supernovae is that it is anisotropic. In fact, it is directed towards the same direction where we see the CMB hotspot, in the same direction where we are seeing the matter dipole hotspot broadly within 10-20 degrees, which means that it cannot be due to lambda or dark energy or whatever. Then the question arises, how is it that people inferred all those things? They did that assuming that the universe is isotropic, FLRW, right? Now, of course, we are not in an isotropic frame. We know that we are moving with respect to the CMB by, whatever it is, 368.9 kilometers per second in some direction. So what people do is when they measure supernova redshifts and luminosities, they first boost to the CMB frame,
I agree. I agree. I
and
agree with
then
you.
they correct for the peculiar motions of the host
Yes.
galaxies of the supernovae. And that then is supposed to give you the right frame of reference in which you can apply the Friedmann-Lemaître equations, extract cosmological parameters, all the rest of it. And what we have just heard from Nathan tells you that that procedure is not going to give you the right frame of reference, because
I agree.
we are seeing that the distribution of matter in that frame is still anisotropic. It doesn't match the CMB. So the entire basis for the assumption that DAISY and supernovae and other analyses make is wrong at 5 sigma. Well, it's not wrong. It is what's the word? Let's say it's challenged at more than 5 sigma, which is good enough, I think, reason to distrust any answers that come out of it.
I would agree with you. I
Well,
just
you agree with me. I'm very happy to hear the TV, but it's just you and me. It seems to
yeah,
me
but
that the rest of the
since
cosmology.
I see Anthony here. Anthony, could I
Yeah.
ask you some? I was thinking that one should make a distinction between lambda CDM model and the observation of cosmic acceleration. So I'm happy to rule out lambda CDM, and I see that there's a pushback when Subir says that the universe is hence the conclusion that it is accelerating is doubtful. From how Subir explained now, I am inclined to agree with him. But that's one thing the community is not willing to give up. So, what is your viewpoint, Anthony? Can we
Um,
say because of this anomaly that hence the inferred cosmic acceleration is in doubt?
well, I wouldn't make that link at the moment myself, but what I was going to ask about is what Subir was just saying about the cosmological constant and isotropy. I mean, Bianchi universes show that you can have something that's an isotropic, but can still have a perfectly good functioning lambda in it. That seems to be in itself a counterexample to what you're saying.
No, no, and even in Bianchi, lambda necessarily any property of the quantum field theoretical vacuum has to obey Lorentz invariance. That
Yes,
is the fundamental tenet.
yes,
But
my
Lorentz invariance is perfectly consistent with the Bianchi universe. That is, there is no contradiction there.
absolutely. So that's what I'm
Yeah.
saying. Yes, I'm pointing out that you can't reject anisotropic universes on the grounds that you've got lambda.
No, no. If the acceleration is being attributed to lambda, then that acceleration must be in the cosmic frame of reference where the analysis is being done. In that frame of reference, it must be isotropic. And we are finding, even after we do the same exercise of boosting to the CMB frame and correcting for peculiar velocities of the host galaxies, etc., even so, there is a dipole anisotropy extending out to about redshift of zero point 0.1, at which up there it dies away, and that is just the kind of behavior you would expect, independently if we are embedded in a bulk flow. I should also say that there was a small isotropic component of the acceleration that could be still allowed within the uncertainties, but recently it has been noted by a group of Korean astronomers, in fact, two independent groups, that there is a correlation of the supernova luminosities with the age of the progenitors. And if you correct for that, then even that monopole component reverses sign, it becomes deceleration rather than acceleration. And you will see
That,
this coming out within the next few weeks in monthly notices.
yes, but I mean, the
We
recent
sorry to
supernova.
interrupt you. We
Mm.
after in a few minutes we'll go to Xavier's question, but I'm very interested in understanding, Anthony, why you said you won't make that link yet, that the dipole anomaly implies that the inference of cosmic acceleration and dark energy is suspect. I want to understand why are you disagreeing with Subir on that? It's very
But
important.
the reason I gave earlier that we simply don't know what's causing the dipole anomaly, and so we cannot say as yet whether whatever it is that's causing it is also telling us that dark energy doesn't exist or in some way. So it's the lack of knowledge that's the question.
But my point was simply that all inference of dark energy makes the FLRW assumption. Do you agree with that?
Yes,
In,
apart from, as I say, it can be a Bianchi model rather than FLRW.
but that is not historically okay.
No, okay.
Let's just so far all the analysis that have been done that claim to find evidence for dark energy from astronomical data, whether it is the CMB or baryon acoustic oscillations or cluster counts or whatever, everything has always assumed FLRW as the basic assumption. And if that is now being challenged, then surely you'd agree that all those claims need at least to be re examined. Whether any of them will survive the re examination remains to be seen.
I tend to think about the dipole anomaly, which we've been hearing about, that it
Yes.
is due to some primordial dipole asymmetry. I tend to think that. I know it's going to be difficult to reconcile values, but that seems most likely to me, and that the FLRW is still doing fine, but the whatever happened initially is preserving some sort of dipole asymmetry.
Okay, then let me ask just one specific question. Otherwise, I don't want to take up too much time,
No.
TV. So, very specifically, Okay, I take your point. In fact, I should tell you that Jim Peebles was also, of a similar mind. Let us save FLRW and say that this anomaly arises from some, I don't know, maybe it's a super horizon, isocurvature perturbation, whatever.
Mhm.
Be that as it may, this anomaly is affecting the galaxies and quasars that we are observing today at
Yeah,
medium redshifts. It is precisely the same observations of these quasars and galaxies by, for example, the DAISY collaboration, which are being interpreted assuming that they are isotropic in the CMB frame. And this is manifestly challenged by the anomaly that you have just heard about. So, how can they continue to make that assumption when this data are showing that that is suspect?
yeah.
And
Well,
then any conclusion you draw from that, whether of dark energy or time evolving dark energy, must be suspect. That's all. It doesn't
yeah,
matter if you have saved FLRW. The things we are observing are the same galaxies and quasars that we are now seeing are exhibiting an anomalously large dipole on the sky. So how can they be subject to the same simplified assumptions that are being made in those analysis papers?
well, it sounds a very good idea to try to estimate the extent of such effects that there will be in
It'll
that
be
analysis.
it's a order one effect because this dipole that you're seeing is twice what it should be. It's not something you can ignore. The first thing you should do is to ask if the DAISY BAO signal is in the same in every direction that they've looked at, which is about 35% of the sky. And
Yeah,
I have not found any statement in any of their papers that they have done this.
no, that,
They have looked at 50 million redshifts and they have not made any statement as to whether that signal is actually invariant even over the third of the sky they have looked at. This is what I
So,
find astonishing.
yeah, look, I can maybe just jump in. So again, there has been a lot of theoretical work since the dipole papers began to at least be taken somewhat more seriously. And it seems to me like we have enough sort of multi-messenger signals here from not just the quasars and radio galaxies, but also from supernova and the so-called Hubble tension and things like that, and bulk flows, that we should, at least in principle, with current data, be able to start setting up likelihoods for different models and including all of these anomalous data and to see, if you allow your velocity to vary and you marginalize over that uncertainty, what happens to your supernova results, things like that. It seems to me like we should be able to do this in principle. We just need some graduate students or postdocs to work on it. But we have the data, right? We're at a point where we're qualitatively discussing how these various anomalies feed into our picture of lambda CDM. But I think what's needed is a self-consistent quantitative approach. And I, I I don't see any reason at first blush, at least, why we couldn't start to do this.
Okay, thank you. Could we take Xavier's question now, please? Yeah, Xavier, go ahead.
Yeah, thanks. I have a very sort of naive question, I suppose. I wanted to try and understand precisely in terms of all this discussion, how far away from homogeneity and isotropy do these results place us? If you wanted to sort of turn these results into a kind of delta rho over rho anomaly, how far away are we from a local FLRW hypothesis?
Well, I can say that if indeed our velocity is 370 kilometers per second towards the CMB dipole direction, that the anisotropy of the moderate redshift universe as traced by quasars and radio galaxies is of order 1%, which is quite anomalous. So, I think that's the best answer that I could provide, at least.
Yes, it's sub-percent. It's
Like
not a it's it
0.
is it, the universe is still largely FLRW. It's a good approximation,
Okay.
but it fails in detail, And that detail is rather important because the inference of dark energy, as I've been trying to say all this time, rests on that assumption being exact. Okay. So 1%, a miss is as good as a mile here.
Yeah. And I mean, this was kind of an interesting. I've seen this. I've seen this comment throughout the literature. I remember in Jim Peebles' review how he mentioned how the lambda CDM, for all its faults, gets a local Hubble constant within 10%, which is a pretty impressive um, prediction. And certainly that's true. But all of in so many cases in nature, all of the interesting phenomena happen at sort of the few percent level, right? Gravity predicts the Earth should be a perfect sphere, but the fact that it's not gives you nuclear decay, it gives you angular momentum, it gives you all kinds of interesting thermodynamic effects. So again, it's lambda CDM has been very good, but maybe it's time to go deeper. And the question is how do you constrain any of these new ideas?
Thank you.
Yes.
Thank you.
That's why I'm always amused when people talk about measuring the Hubble parameter to better than 1%, because that's like asking what's the radius of the Earth to better than 1%,
Yeah.
ignoring the fact that it is not a sphere, but a geoid, as you just said. It's got valleys and it's got mountains, it's got trenches, and those deviations are more than 1%. So it makes no sense to talk about something like the Hubble parameter, which presumes that there is a spherical, contour which you are measuring. It is not spherical, it deviates by several percent across the sky because of these bulk flows and other things we heard about. But somehow there is this assumption that underlying all this mess, there is some kind of a pristine, FLRW universe, which is actually, to talk about it in those terms, is itself anathema in general relativity, because you can't just treat it as a kind of a Newtonian universe with perturbations on top. That it's fundamentally different in relativity. But leaving that aside, I'm just saying from a measurement point of view, people just have to ask yourself, when people say that somebody has measured the Hubble parameter to 1%, that is saying that there is something like h sub 0. It doesn't depend on direction, it depends only on the epoch, on the redshift. And therefore, if I plot all the velocities around me, the three-dimensional surface of constant velocity should be a sphere. And we very well know that this is not so locally. Andromeda is falling towards us. It's not a redshift, it's a blue shift. So then the question is, how far out do you have to go before it actually becomes a smooth enough sphere, say to within 1%? And that is a long way beyond the point at which you are calibrating the supernovae with the CFETs. That is where this Schu's collaboration is claiming to make a sub 1%, sub% measurement. And yet, as people said, there are hundreds and hundreds of papers about the so-called Hubble tension, maybe because it's easy to write an explanation for it, but this dipole anomaly is like totally incomprehensible, difficult to get on top of, and certainly very hard to toss off a paper about, with some manufactured interacting dark energy or something or the other. So
Yeah,
anyway,
that was one thing
that's
I
my
forgot
pet
to,
peeve.
that was one thing I forgot to mention, but we did, I think, comment on it in the colloquium, is that the Hubble tension and the dipole anomaly both reached the 5 sigma level within a few months of each other, and were both published in the same journal, AppJ Letters. And yet, paper published by that's something like 10 times the citations, even though both anomalies are and still believe still are of equal significance and of equal consequence to lambda CDM. So I find that very interesting from a sociological point of view.
Well, as Peebles commented in that paper by him in 2022, you quoted, I can't remember the exact words, but he said something about that there are hundreds of citations of the Hubble tension and very little discussion of the dipole anomaly. This is something about the sociology of the field. He uh, actually, I was a bit surprised that he would make a comment like that, because it's the kind of thing that, if I said that, people would jump on me and say I'm being, prejudiced or biased. But people said himself that, this is a sign of, let me see, yeah,
The
I
way we,
expect the difference is an inevitable consequence of the way we behave,
the
says,
way we behave, yeah.
yeah.
Yeah, I mean, I think
Yeah,
some of it has to do
one
with,
other point, Subir. So sorry to interrupt you.
Yeah.
So on the issue of homogeneity, also it is probably true that even going up to 150 or 200 megaparsec, we are not seeing, we are seeing structures large enough which contradict the assumption of we have not found the scale of homogeneity yet.
That's
That's
correct. That's correct, because the latest analysis of that has been done by Silos Labini, and I'm trying to find the paper. This came out just a couple of months ago. He did an analysis of DAISY. Oh yeah, here it is. I'll paste it in the chat for your thing. So he says, uh, where is the chat? Oh, here it is. So they looked at the DAISY data, which is the most detailed to date, and they find that up to the scales proved by DAISY, which is 400 over little h megaparsecs, our conclusion is that the galaxy distribution does not undergo a transition to spatial homogeneity within the proved scales up to 400. In fact, they see a transition to a power law r to the minus zero point 0.8 without exhibiting any transition to homogeneity. And this is basically the biggest volume that has been proved so far. Previously in SDSS, there had been a claim that they had seen the transition to homogeneity at about 100 megaparsecs. But what these people show is that that was a finite size scaling effect. It was not a real transition. This is also a puzzle.
would this constitute independent evidence in your support that the inference of dark energy is suspect? Does the not finding a homogeneity scale is also
Of
a
course,
problem for?
yeah, this is true. Except that what happened, well, the situation here is so bad that before DAISY data, I recall there is a widely cited paper by the Wiggle Z collaboration, and they had an extremely convoluted survey volume. So therefore, the basic test, which is very simple, it was suggested by Silos Labini's collaborator, who is a condensed matter theorist, and he said, look, you just put spheres and you select a galaxy, and then you put a sphere around it, and you count how many galaxies there are in that sphere, and then you increase the size of the sphere, and you ask how do the numbers scale. And if the numbers start scaling as r cubed, then that means you have reached homogeneity, right? So this makes no a priori assumptions at all. The only problem is that you're now talking about reaching homogeneity on the scales of 100 200 megaparsecs. So you have to put spheres 200 megaparsecs big within your survey volume, right? And
Yes,
you would have
yes.
to put a large number of them, because unless you put lots of independent spheres, you're going to have a lot of short noise. And unfortunately, no survey to date has been large enough to actually see uh, this, because what was happening, especially in Wiggle Z, is that the sphere was coming out of the survey volume. So there was a large part of it outside the survey volume. So what did the analysts do? They filled the bit of the sphere that was outside the survey volume with galaxies drawn from a random simulation, and that simulation by definition is homogeneous. So they actually were putting in the answer that they find, and then they report we have seen the transition to homogeneity at 100 megaparsecs, but actually they couldn't say that because the survey volume wasn't big enough to say that. And now the DAISY data, which is a much larger volume, gives us the opportunity, as discussed in this paper by Silos Lavini. It's published in Astronomy Astrophysics just a month or so ago. And it makes it quite clear that there is still no transition to homogeneity up to 400 megaparsecs. And that is also a challenge for the standard paradigm.
I agree. Thank you. Thank you for this. Yeah. Nathan, you want to say something more?
Oh no, I was just going to make a further sociological comment, but there's an apocryphal, almost certainly an apocryphal story about how when uh, either the Dutch or the Portuguese first sailed to the Americas, that the natives were literally not able to see their ships because of how alien they were. And I sometimes wonder if the fact that the dipole anomaly does not seem to fit neatly into any simple extension of lambda CDM or FLRW, or any systematic perhaps, that is one of the reasons why it's been rather undersung given its significance,
I
because
agree.
it's kind of hard to see it in a sense, even though the data are loud and clear.
The more you shake the paradigm, the harder it is to get acceptance.
I should remember that. Well, I'm sorry, I was brought up to believe that, we do science. We are not selling used cars here. But okay, never mind.
Yeah. Okay, great. Any more questions, please? So nice of you to stay on for this great discussion. Any more questions, please? Hi, Jose. Good to see you. Okay, so should we wind up? Subir, Nathan?
Thank you.
Yes, thank you. This has been great. This has been a
Yeah,
real
yeah,
pleasure.
we love it. Yeah, yeah. It's great fun.
Yeah.
Yes.
This was
Thank
So,
you for the great talk.
Thank you.
thank you. So I will close the session now. Please see you 2 weeks from now, Jason Blood. I think that's standard model of particle physics, quaternions, octonions, that kind of stuff. So
Okay.
thank you again, Nathan, for a really beautiful and lovely talk. Apart from the discussion, the talk itself was very clear and enjoyable. It hits you in the face that okay, there is an anomaly. I think that is being accepted, though it's not being given much attention. I agree, but nobody is denying. I think that it is there.
And he's a proper astronomer, not a theorist like us.
Yes, yes, yes. He kept
I,
clear
I,
of theory. Yes.
I do have a day job that's completely unrelated, I assure you.
Okay. Thanks a lot.
Thank you.
Bye then.
Thank
Sure.
you very much.
Take
I
care.
say good night to you. See
Good
you
night.
next time.
Bye.
Bye
Bye.
bye.
Bye.